Hello, friends. Welcome to another session on Quant. I am Marco, and if you are first time in this channel, then what we do here is basically talk about quant topics that are relevant for your CAT, NMAT, SNAP, IIFT kind of exam. So we have just covered the fundamental session on base system, and then we'll do one problem session on base system. There are not many varieties of problem. Whatever the different type of problem, we'll take one each and try to solve. But as the thumb rule goes, if I do 6 or 7 problem now, you have to do 3 times around 20 problems at home from base system. And if there are any doubt wherever you face, you can drop me a comment in this video or drop me a mail in the mail ID given in the description box. And from there, I'll be able to guide you. But yeah, that 3x number of problem solving is very much required. And the second thing is, once I start showing you a problem, don't continue the video. You can pause the video, try it at your end for a couple of minutes. If see if you are getting the answer. If you are not, just continue, see my solution, or even if you get the answer, see whether you have done it right or wrong by seeing the solution, or is there a better approach to do it. So these are the two things I want to convey before we start this problem sessions. But the other thing is, please go through the fundamental session video that I will put in the description box before we start solving the problem. So just to summarize, these base systems are basically, we normally talk about base systems of 10, the normal numbers that we see in the world, 0 to 9 are the different digits we have. Similarly, we don't do it on a regular basis or in our daily routine, but there are other base systems also possible, like computer understands binary, where there is only 0 and 1. So you can define every number that you can define in decimal, or let's say 529 have a binary equivalent representation of it. Similarly, I can think of a base system of 7, or I can think of a base system of 13. You can think of any base system. The idea is every number, decimal number, can be converted to a particular base system. How to do that conversion, or from a base system, how to convert to a decimal system, that we have covered in detail in the previous video on the fundamental topic. Please go through that. That is very much prerequisite of before solving this problem sessions. So without further ado, let's get started. So let's see the first problem. It says, how many 4-digit numbers in octal systems? So first understand what is an octal system. So an octal is basically base 8. So the numbers are there from 0 to 7. So in an octal system, how many 4-digit numbers in an octal system are also 4-digit number in a decimal system? So in an octal system, I know the numbers are from 0 to 7. Can you tell me what is the smallest 4-digit number in octal system? Smallest 4-digit in octal will be, the smallest 4-digit will, when all the digits are 0 and the first digit is 1. This is the smallest 4-digit number in octal system. Similarly, we think what is the largest 4-digit in octal system. So this is in octal system. And when you put 8 like this, that means it is the number is of base 8. There you have 1000 in decimal also, you have 1000 also, binary also. So unless you put this 8, it doesn't mean it is an octal system. By putting that 8, I am mentioning the base of that number and what base system I am using. So the largest 4-digit I can think of is 7777, because 7 is the highest number in octal system, like 9 is the highest number in decimal system. So they said between 1000 to 7777, how many of these are actually a 4-digit number in decimal system? Because they said how many 4-digit numbers in octal system are also 4-digit number in decimal system. So first, let's see what is the smallest 4-digit number in octal system we know, and what is the equivalent of that in decimal system. So we know 1000 to 8. We start from this 0. So 0 into 8 to the power 0. 8 is the base. Then the next 0. 0 into 8 to the power 1. Plus next the third 0. 0 into 8 square. Plus 1 into 8 cube. we do, it will get 512. So obviously 512 is not a four-digit number in decimal system, or decimal means base system 10. So we'll start from 1000 and let's see what is 7777 in base system 10. 7777 is basically 7 into 8 to the power 0 plus 7 into 8 to the power 1 plus 7 into 8 square plus 7 into 8 cube. Okay, so this is 7. This is 7 8 is 56. This is 49 into 7. That is 340. Oh, sorry, this is 64 into 7. So 64 into 7, 4 7s are 28. 508. Yeah, 64 into 7 is 508. Okay. And then you have 512 into 7. So this is 63 plus 508 plus 54, 35. So your answer is 3, 8, 11, 4, 15, 1, 6, 7, 5. So 4155. Yeah. So this is 4155. Just let me see the sum again. Yeah, just a minute. Okay. So there is, I think, one mistake here. It's not 508. 64 into 7 gives me what? 448. Sorry, this is 448. So what we'll get here is 448. Okay. So you get 448. So this is 663. Sorry. Plus 448. So your answer will not be 4155. It will be 4095. Yeah. So we have 4095. Now we know 512 is the smallest in decimal, and 4095 is the largest in decimal, which are four-digit numbers in octal system. So basically 512, 513, 514, all that numbers in decimal system is a four-digit number in octal system. So the first number we should consider in decimal system is 1000. This 1000 and this 1000 don't get confused, because this is in octal system, which represents to 512. This represents to 512 in base system 10, and here I'm talking about the actual 1000 of base system 10. So from there till 4095 in base system 10 is have all the four digits number that are four-digit number in octal system as well. So your number of numbers will be 4095 minus 1000 plus 1, because both are included. So that is 3096 is your answer. So there are 3096 numbers which are four-digit in octal system as well as four-digit in decimal system. So basically we got the highest four-digit number in octal system and we got the smallest four-digit number in octal system converted into a decimal. Then we see the smallest four-digit number in octal system is not the four-digit number in decimal. So then we have to see from where we should get the first four-digit number in decimal system, which is 1000, and from there till the largest four-digit number in decimal, which is equivalent to the largest four-digit number in octal system, which is equivalent to this 4095 in decimal system. Okay. So then we see 4095 to 1000. How many numbers are there? There are 3096 numbers. Hope it's clear. If it is not clear, please drop a note. We'll be able to help you. The next problem, it says 1255 whole base 6 is 503 whole base k. So again, the whole idea is to convert it into both of these into a decimal number. So 1255 whole base 6, when it converted to a decimal, it will be 5 into 6 to the power 0, 5 into 6 to the power 1, 2 into 6 square, plus 1 into 6 cube. So that means 5 plus 30 plus 72 plus 216. So that means 35 plus 72 plus 216, which is equal to 323 in base system 10, right? 323 in base system 10. Okay. So this is 5 into 6 to the power 0, 5 into 6 to the power 1, 2 into 6 square, 1 into 6 cube. Okay. 323 in base system 10. Similarly, 503 in base system k can be written as 3 into k to the power 0, 0 into k to the power 1, plus 5 into k square. So that is written as 5k square plus 3, which is also in base system 10. K to the power 0 is 1 and k to the power 1 multiplied by 0 is 0. So can I then write 5k square plus 3 must be equal to 323. So that means both of them are in base system 10. So 5k square must be 320. Means k square will be 64. That represents k as 8. Obviously, k cannot be a negative number because k is a base. So that means 1255 whole base 6, that is in base system 6, is equivalent to 503 in base system 8. Okay. It's just straightforward. So the idea is whenever you have multiple base systems, try to get everything in a decimal and then try to calculate, because that's where we are more used to, and it's easy to convert any base system to a decimal. Let's move to the next problem. Rajiv found a decimal number which has been represented in base 3, 4, 5, 6 and ends in 2, 3, 4, 5. Okay. Now, there is a decimal number. Let's say the decimal number is XX in decimal number, which Raju is trying to convert. And when it is converted to base system 3, the last digit is 2. So that may be 2 when it come to base system 3. Then it come to last digit as 4. Oh, sorry, last digit as 3 when it is base system 4. Then it comes to last digit 4 when it is base system 5. And then it also equal to last digit 5 when the base system is 6. So if you see, the last digit is always 1 less than the base system that has been converted to. Now, if you think typically, how you get the last digit of any number? Think of, I'll tell you with first base system 10. If you have 123 in base system 10, the last digit is 3 here. How will you get it? The other way of getting it is if you divide 123 by 10, you get a remainder equal to 3. So basically, can I say and think this and apply this with every logic? Any number when divided by the base always gives the last digit as remainder. You take any number. You take 371, 579. If you divide by 10, you will get only the last digit as the remainder, and that is actually true for every base system. Not only for 10, you can take any number and try to divide. You will only get that number as a base system. So for example, if I write, if a number is in base system 4, let's say 1, 2, 3, the number is in base system 4. If you try to divide this number 1, 2, 3 by 4, you will always get a base system or remainder as 3, which is nothing but the last digit. So the last digit is nothing but when a number is divided by the base system. Okay. So in this case, then we can say when divide by 3, you get 2 as a remainder. When divide by 4, you get 3 as remainder. When divide by 5, you get 4 as remainder. When divide by 6, you get 5 as remainder. So it's always 1 less than that. So basically, then the smallest such number, if you recall the number system class where we said a number when divided by 3 gives a remainder 2, divide by 4 gives a remainder of 3, divide by 5 gives a remainder of 4. What is the smallest such number? So basically what I'm trying to say is whenever you divide a number with a different set of numbers and every time you get a remainder, uh, in which case the gap of the remainder and the divisor are same, you can go back to the number system class where we talk about the smallest such number. Smallest such number is always LCM of the divisors. LCM of, in this case, it will be 3, 4, 5, and 6, and minus 1, which is the difference of the remainder in every cases. So when your divisor is 3, your remainder is 2 because 2 is the last digit. When your divisor is 4, your remainder is 3 because 3 is the last digit. When your divisor is 5, 4 is your last digit, 4 is the remainder. So every case the gap between the remainder and the divisor is constant. This is a theorem we covered in number system. Whenever a number is, again I'm repeating, whenever a number is divided with a set of numbers and in every case you get a remainder from which the gap of the divisor and the remainder is same in every case, then it's the smallest of such number is basically LCM of the divisors minus the gap. Okay, so in this case it will be 60 minus 1 or 59. 60 is the LCM of 3, 4, 5, 6 and 59. The smallest such number is 59. Actually, you can write this as a generic form of 60k minus 1. So the next such number is 120 minus 1, 120, 119. Then the next such number is 16 to 3 minus 1, 179. So that, but the smallest such number is always the LCM. Okay. Or you can think of this number as LCM of 3, 4, 5, 6 into k minus 1. When k is 1, you get the smallest such number. When k is higher, you get the next set of numbers. So this always remember 59 is not the only number, it's the smallest number. The next number will be 60 into 2 minus 1. The next number is 16 to 3 minus 1, so on. But the idea here is there are two things we covered very important in this topic is whenever in any base system you divide the number with the base system, with the base value, you will get the last digit. So that we learned here. And the second one is whenever, and this is a refresher of your number system concept, whenever number n, I'm just writing number n gets divided with a, b, c, and every time you get a remainder of r1, r2, r3, the gap between a and r1, b and r2, c and r3 are always same. Then the smallest such number is LCM of a, b, c minus the gap. What is the gap between a and r1, b and r2, c and r3? So here the gap is 1 and the divisors are 3, 4, 5, 6. So we did LCM of 3, 4, 5, 6 minus 1. Please revisit the number system session, the number system playlist. You will be able to understand this is a very common theorem of the division rules, okay, or the remainder theorems. So yeah, please revisit the remainder theorems session on number system. We'll be able to understand this. Okay, the next problem, Kiran wanted to weight 324 kg of weight. The weights are available in denomination of 1, 2, 4, 8. Okay, so can I see the weights are in power of 2? 1 is 2 to the power 0, 2 is 2 to the power 1, 4 is 2 square, 8 is 2 cube. Okay, he decided not to use more than one weight for each denomination. Okay, how many weights does he use in all if one side balance is used for weighting. So since one side balance is using for being weight, so you can't use two weights simultaneously, both the sides simultaneously. So he will, so he has weight 1, 2, 4, 8, 16, 32, all the power of 264 and so on. Okay. Now he will either have to play use a particular weight, either use 1 kg, 2 kg, 4 kg, or not use it. There is no separate way. Okay. So if he and he has to get 324. So can I think it this way? So 324, if 324, which is in decimal, if I, rather than 324, let's keep it an easy number. Let's say 4 kg he has to weight. Now, for 4 kg, he can directly use the 4 kg weight. But how will I arrive that? Now, if you think this 4, remove that kg, this 4, and this 4, if I convert it into 10, which is decimal system, which is already there. If I convert into binary system, it will become 100, right? 100. So that means 0 represents the 1 kg weight, which is not being used. The next 0 represents 2 kg weight, which is not being used. 1 represents the 4 kg weight, which is being used, which is 2 square. So which is same as writing 1 into 2 square plus 0 into 2 to the power 1, 0 into 2 to the power 0. So if you see, these are nothing but with a base system of 2, right? So the weights, the sequence of the weights that is available with Kiran is the sequence with the power of 2. That means the number that you need to use is a base system of 2. And then you see which of, where there is a 1 and you can use it, that weight. Where there is 0, you will not use that weight. Let's take any other different example. Let's say he has to weight something which is 12 kg. So 12, 10, if I divide 12 into a binary number, let's say 2 divided 6, so 0, 2 by 3, again 0, 2 by 1, so 1. Okay. So that means 12, 10 is nothing but 1100 in 2. So that means he has to use 1 into 2 to the power 3 plus 1 into 2 square plus 0 into 2 to the power 1 plus 0 into 2 to the power 0. So that means he needs to use this 8 kg weight and this 4 kg weight. He will not be using the 2 kg weight, this 2 kg, because this is 0, and the 1 kg weight, which is also 0. So you use this 8 kg and 4 kg weight. Similarly, if you convert it into 324 in base system 2, you will be able to see wherever there is 1, he has to use that. Wherever there is 0, he should not be using that. So can I expect you to do the same? You try this problem, try to convert 324 base 10 into a binary system and see wherever there is 1, he has to use that weight. Wherever there is 0, he will not be using that weight. So number of ones will represent how many weight he has to use. So here he has to use 2 weights, which is 8 kg and 4 kg. In the previous one, he has to use 1 weight, which is 4 kg. So wherever there is 1, how many number of ones, that represents the number of weights he has to use. Can you tell me how many weights he has to use by converting 324 base 10 into binary system? And what are the denominations of those weights that he is going to use for 324? Please do this and drop a comment by your answer. Okay. So this is problem number 5. You can, or problem number 5, and you can just drop an answer in the comment section and let me see how many of you are getting it right. Okay, let's move on to the next problem. Find the value of 1 with base 2, 2 with base 3. Okay. So if I have to write 1 with base 2, 2 with base 3 with base 4, and so on, n with base n plus 1. In this case, we can write 1 into 2 to the power 0 because there is only one digit, plus 2 into 3 to the power 0, plus 3 into 4 to the power 0 because these are the only digits, plus n into n plus 1 to the power 0. So that means if I try to convert it into a decimal system, it will become 1 plus 2 because 1 into 2 to the power 0 is 1, 2 into 3 to the power 0 is 2, 3 into 4 to the power 0 is 3, so on. It's n in this system stem. So this is nothing but n into n plus 1 by 2 in this system. Okay. So I hope this is clear. So which may look complicated, but if you try to start converting into decimal system 10, things start falling in place. Okay. This is also a quick concept problem. N1 is a 3-digit number in base 11. A new 3-digit number N2 is formed by rearranging the digits of N1 in some order. The difference between N1 and N2 is always divisible by. So 3-digit number in base 11. First, let's understand the functionality in base 10. So let's say N1 is a number which is in base 10. So how will I write N1? N1, let's say 129. And N2 is formed by rearranging the digits. So N2 will become 921. By rearranging here means completely flip the digits. So 129 becomes 921. So the difference between N2 and N1, N2 minus N1, you will calculate and see what it is always divisible by. So for example, if I do it generic number, and that will be easy. So let's say N1 is nothing but XYZ. So I can write this as 100x plus 10y plus z. In that case, this will become zyx, or I will be able to write 100z plus 10y minus plus x. So if I do a subtraction here, I get 99x minus 99z. So that means, that means it will be 99 into x minus z. Okay, 99 into x minus z. So for a 3-digit number, it will always be divisible by 99 when it is that, or we can say it is also divisible by 9, which is 11x minus 11z, because 99 is not a digit in itself. 99 is a number using 9 and 9, which are individual digits. So I can say this is divisible by 9. Okay. And now I will take another 3-digit number, which is another base system, and I'll try to convert. So let's say 1, 2, 3 in base system 4, and 3, 2, 1 in again base system 4. So again, if I try to convert this, so this will become 1 into 4 to the 4 square, 2 into 4 to the power 1 plus 3. 3 into 4 to the power 0, which will become 1. That means 16 plus 8 plus 3, which is 27 here. Is 27 here. 321 to the power 4 will become 3 into 4 square, 2 into 4 to the power 1 plus 1 into 4 to the power 0. So that means 48 plus 8 and 1 is 1. So 57. So 57 minus 27 is 30. 30 is divisible by 3 as well. 30 is divisible by 3. So what I'm trying to build is, whenever you have a number in any base system and you try to completely flip the number and take the subtraction between the actual and the flipped number, the number is always divisible by 1 less digit than the base system. So if it is a base system 10, you can get it divisible by 9. When it is base system 4, you can get it divisible by 3. You may say this is also divisible by 2. 30 is also divisible by 2, but that's not the standard form. 3 is what we are looking for. Similarly, you take any number, you take a number in base system 7 or base system 8, you will see that the number and the flip digit of that number will always be divisible by for base system 7 6, for base system 8 7. So the difference between n1 and n2 will always be divisible by here 11 minus 1 10, because 11 is the base system, so 10 will be the number which will always divide the base number that is in base system 11. Okay, so hope it's clear. You can take any number, you can take, let's say, 1 to 7 in base system 11, and by flipping that number you get 7 to 1 in base system 11. First, both convert this number into base system 10 and subtract, and then you will see the number will start getting divided by 10. Okay, so I hope things are clear. We have solved quite a few different type of problem in base system. If you have any further doubt or any questions that you find it difficult, you can ask me in the comment section or drop me an email. I'll be able to help you. Till then, please go through the fundamental session and then this, and hope this session was helpful. See you next time. Thank you. Bye.